Welcome to a new episode, everyone. Today we have a second session with Laurent. So we had a session a while back, and today we're following that up with additional details on the same quantum information networks that we were discussing last time. Because we didn't have time to cover all the details, we're going into some more depth today, partially on some of the conceptuals around how a system like this is implemented, and then also the future of these kinds of technologies. I hope you enjoy it. Yeah. So to kick this off, we're looking at the article now that you published in Nature. I would like to focus primarily on this graph that we can see now. So this is sort of a representation of a quantum information network in sort of a conceptual way. This is a little bit different from what we discussed last time. So last time we were very heavily focused on the nitty-gritty details of how we generate entanglement, how we would sort of link multiple satellites together in case we want to transfer this information. How does that fit into the larger picture of a diagram like this, consisting of these three layers? Would you mind explaining what the rationale is behind producing this kind of figure and what how it links to the topics that we were discussing last time?
Yes, okay, so of course. So in fact, here in this picture, you have to understand that this is not the quantum link, in fact. So this is an architecture for, so we call this a subsidiary organization for a quantum information network based on software-defined networks. So this is an architecture of who is the master and who gives the order to drive the network. Because in a quantum information network, keep in mind that you have a lot of equipment, devices, quantum devices, and classical devices. And they all have to work all together. And if you think about, for instance, what is happening in Europe, if you think about France and Germany, for instance, that means that you have to synchronize many networks with ground networks and space segment. And you have to define who will do what and when. And so you need an architecture for this. And here, what we propose is the subsidiary organization, such that you refer to a controller of an upper layer that will decide who will be synchronized with whom, because you have to define a path, for instance. And the path, this is a very complex task. Because if you have a space segment, you have some nodes that are moving in the network, and so you definitely need someone who will decide which path to take. And so this organization has the advantage to have an authority who will decide who will be used, which node will be used to ensure that you have a transfer of quantum information.
Mm-hmm. Okay, so very concretely, to put this into context now, we have the subdomain levels. They would then be tied in that case to physical satellites that are orbiting somewhere, and the idea behind this figure is as you escalate up the hierarchy, you would have more higher level controls at the supercontroller level, and then the subdomains would keep track of their own satellites. And as satellites then traverse across the globe, for example, they would switch subdomain, or how would that work? Is this sort of a static... can you think about this geographically, at least the subdomain level, that you would have some geographical entities that are tying to satellites in their vicinity, or am I thinking about that in the wrong way?
Yeah. So what I can say is that for the subdomain levels, so N1.1, so if you take the lower layer, you can think that it could be different countries managed by different society or network providers, and so and these networks could involve satellites or not, in fact. But here we suppose that the satellite is coupled to all the ground networks. And so I don't know if it answers to your question, but this hierarchy is in fact one hierarchy that will ensure that you can have upper authorities. So you can think about Orange in France and Dutch Telecom in Germany. And so we have to think about someone that will be able to manage both network. So this is like network controllers, and these network controllers will have a sufficient visibility on the available nodes on all the networks. So this is more. How can I say this? This is more a functional picture here. So that does not mean that the green bubble is a satellite. Huh?
Right. No. That's clear. That's clear. And I think you answered the question on a generic level. What I'm asking, so let's stick to the picture of the blue subdomain levels being corresponding to a nation, let's say, or a country. Is there a preference in the physical implementations of these kinds of systems? Like, let's take current satellite architectures, for example, and the way those are managed by countries. Do countries generally have satellites associated with them? Like, let's say, ownership of particular satellites, and those satellites are within the control of that subdomain all the time? Or would that be more of a geographically based structure where countries, for example, have agreements to be responsible for the satellites that are within their vicinity and make sure that they have sort of control over those? Maybe this is a very naive question, but from my perspective, I'm not sure which of those would be sort of the natural way of trying to manage a complex set of satellites.
Yeah, so in the project we are working on, we are discussing this, and there is no definitive answer to this. In fact, we can think about the space segment as a domain itself. So it could be a domain itself, and so we are discussing this. In fact. Okay. Yeah.
As a slight follow-up to the three levels or layers that we can see in the figure here, there's also a mentioning in the paper of 4 main segments, and I'm assuming we're referring there to a slightly different concept, but I had some problem grasping what that concept was. So we have the mission segment, the control segment, and the space segment, and the access segment.
Yeah.
Can you summarize what those mean and how they're different from the layers that we're discussing in this kind of figure?
Yeah, okay, so the segments, so typically for space applications, this is clear that the satellite belongs to the space segment, but the satellite is controlled at the ground with telecommands, and so you need stations for this, and so you need a control segment. So you need devices that are somewhere at the ground, and who are used to send. So this is like antenna. In fact, this is our antenna, and these antennas speak with satellite, with antennas on board the satellite, and so this is called the control segment. The control segment. This is all the device with the control center, and in fact, here this picture show how all the. So this is like organs, and they are working together to such that the whole system works. And so this is very generic to speak about the space segment for the satellite, the control segment for the control center, and the ground telecommand and telecontrol stations. And the control center receives all the mission instruction from the mission center. So the mission center is all the intelligence to control all the people. In fact, so this is like the brain. And
would this correspond to the supercontroller layer in general?
Yeah. Okay. So it could be included in the mission center. But maybe not. So this is not yet defined.
Okay.
Because you also can think about the upper level could be included in the network controller. So so it could be either in the mission center or in the super network controller, let's say.
And what's the conceptual difference between those two modules? Why are they separate and not just one, let's say, one mission center that contains also the super network controller inside of it. Is there a reason from an architectural point of view to separate these two?
It could be, but I think the main reason is the ownership. At some point, you have a business and you have societies that provide services, and so they claim that they want to have the control on some functions of the system, and so they request to include some of the function in their own building, for instance.
Okay, so what kind of tasks would be split between the mission center compared to the super network controller?
Yeah, so the mission center, this is the brain that controls everything, let's say. But still, all the ground functions could be delegated. So some functions could be delegated to the super network controller, such that the super network controller mainly focus on the driving of the ground part, based on the mission center instructions.
Okay.
So
would it be similar then to the control center, I guess, for the satellites here? Because I'm assuming this one also has to do with transferring, let's say, high-level mission instructions from the mission center into concrete, let's say, actions for, I don't know, for control in some way?
Yeah. Yes, because at some point you have to think about this is a business and there are stakeholders, and for instance N11, if you see at the ground, the sub-network controller N11, it could be Orange in France, and N12 could be Dutch Telecom. Okay, so and these entities will not agree to show all the data with Orange. So Dutch Telecom, for instance, has its own network, and they clearly will not exchange all the information concerning their own networks. And so you have some so you have a separation of the entities, of the stakeholders, and so they have to work together, but they will clearly not exchange all the data concerning their network. And so you have to find the good level of exchange to ensure that they can work together without having the global visibility of the network of the other company. So
okay, so the link, I suppose, that's labeled network control and data here would be, let's say, a link that contains the necessary information to run control from the super network controller, but only that kind of information as well, not any additional information containing, whatever these networks might contain.
Yeah, for instance, here we assume that there are different entities, different companies, but still there is an authority which is called the super network controller that will ensure the subsidiary organization. Because at some point, if they disagree, you have to find a way to work all together, and then you refer to the super network controller. So he will decide not on the business part, so the business will be clearly defined at the very beginning, but it will decide on the functionalities and how to work.
Okay. If we think about the upper path here again, so we talked about the control center a little bit before. We have a connection between these satellites then and the control center. In terms of the information being passed between these two, what is that generally? What kind of control information do you need to send to the satellite to be able to operate a system like this?
Yeah, so typically you have the telemetry and the telecontrol. So the telecontrol, there are telecommands to say to the satellite, now you have to move because the orbit, you have some modification on the orbit, and you have to control the orbit to correct the orbit. So for instance, one telecommand could be ignition for for motor 1 to ensure that the satellite correct its orbit, its altitude. So this could be one type of telecommand. This could be also telecommand to the payload to say now you have to switch on the laser. So the laser should be switched on, and the telescope should be should point to station 36 in France, for instance. So this is a telecommand. So this is like you know when you have a telecommand car, and when you play with your telecommand car, this is exactly the same. You send telecommands to drive your car. Here you are driving a satellite with telecommands, and so all these telecommands refer to the either to the payload or to the platform. So this is the two parts of the satellite.
Okay, understood. No, that's very helpful. I think that clarified a lot of the theoretical aspects that I wanted to bring up in this discussion. I have some more questions on both the example that you presented last time, so the actual experimental implementation of this, and also, let's say, the future then scope of these entire quantum information networks and sort of the architectures associated with those. Would you want to maybe switch over to presenter, and then we can have a look at the presentation where we'll talk about those?
Yeah, sure.
Okay, great. Okay, good. So here we have the experiment. You discussed this in the last session that we conducted, which was essentially your experimental implementation of a quantum information network. Could you maybe just recap very briefly what you did there? I have some follow-up questions, but I think it would be good just to give a couple of minute summary of what this experimental setup included and what you did in the experiment.
Yes, so the setup was one satellite with quantum entangled photon source on board, and the mission is to distribute the entangled photons to Paris and Nice, and we have performed simulations over 1 year, because this is important because you have seasonal effects, and we took this effect into account. And the main purpose of the paper was to compare many possibilities in terms of orbits, wavelengths, detectors, and so on. So that was the main purpose, was to perform a system study to find what are the better choice to ensure the mission we target. And the mission we target is entanglement distribution from space to the ground.
So you have very, very well summarized four key takeaways of your selections. Can we maybe talk about those for a little while? Starting with the first being downlink configuration. If you could describe what that kind of design principle is, downlink versus uplink, and what the reason was for you choosing downlink in this case.
Yeah. Okay. So you have to think about the first consideration is that when you decide to include a device on board a satellite, you have many constraints. So the first constraint is that you will launch the satellite with with a launcher, and the launcher you have lots of vibrations, and so you have to ruggedize the device such that it will survive to the launch. So that's the first point. Then you have pyro explosion due to the fact that when you deploy the solar panel, you are using pyro. So that means that you have shocks. You shock the satellite, and that's not good for the payload. So you have to take into account the fact that you have lots of vibration during launch, you have shocks, and then you have radiations, and you have mecha and thermo effects, so thermal effects, because for a low Earth orbit, the satellite is either in the night because of the Earth, or exposed to the sun. And so that means that you have a gradient, thermal gradient, to take into account. So so that's complicated to put something on board a satellite. So typically what we do, all the devices that are critical, we try to put them at the ground. So if you think about SNSPD detectors, so SNSPD, this is superconducting single photon detectors. So that means that you have to cool down the detectors to 4 Kelvin. So you need a cryo cooler, and that's very complicated to put them on board a satellite. So you have this kind of consideration to take into account, and in fact we converge to the fact that it is better to put the detectors at the ground and to put the source on board. And so that becomes a downlink configuration. And there is also problems coming from the atmosphere. In fact, the worst that you can do is to send light from ground to space, because you have turbulence effects, particularly during daylight. And the turbulence, this is an impairment that disturb the line of sight. So when you target the satellite, in fact, you have a deviation of the light due to the turbulence, and this is worse. This deviation is worse from ground to space than to space to ground.
Do you have a conceptual understanding for why that is?
Yes, okay, because these effects could be you have a counter. How can I say this? You can compensate all the disturbance of the atmosphere by using adaptive optics. So if you have adaptive optic system, then you can compensate with a deformable mirror in real time. You can compensate all these effects, and you can do it. This is easier to do it in a downlink configuration, because you receive some light from the satellite that is used to analyze the wavefront and compensate these errors by using a deformable mirror. And in fact, this compensation is better in a downlink than in uplink, because in uplink, to compensate these impairments, you need a beam coming from the satellite to the ground, and when you use the beam that is coming from the satellite, when you use this beam to correct an uplink beam, the problem you have is that the satellite has moved. So you are doing something that is called point ahead. So you point ahead, and when you point ahead, you have an angle between the received light and the emitted light. And so, in fact, the turbulence is not exactly the same, and so you are not able to compensate exactly the turbulence effects in uplink due to this effect of point ahead.
Okay, and in a downlink configuration, then my understanding right now is that the requirements in terms of infrastructure that you actually need to put in the satellite is much lower than for an uplink. Can you maybe explain very briefly the difference in terms of what you require to actually put physically inside of the satellite in an uplink versus downlink configuration? Because we mentioned all these requirements, like you need to have something that's resilient against like vibrations, against shocks, against all these things. So it seems to me that you're implying that in a downlink configuration, you need to put a lot fewer components actually inside of the satellite. Is that true?
Yes, it's true. So in this configuration, in fact, what you need to put into the satellite, so what composes the payload is mostly the untanked photon source and two telescopes on board. So you don't need to embark into the satellite single photon detectors, or if you need to do it, this is just for for monitoring purpose, and so you don't need to have a very efficient detector on board.
Mm-hmm.
So the mission that does not does not depend on the performance of the onboard detector. So that's important to think about that. That we do not we do not have single photon detectors that you can put on board a satellite. We have to develop it. People have tried, and in fact, Singapore, the spectral company did it with Spooky, and they have published a paper when they analyzed the decreasing of the performance of the single photon detector on board.
Mm-hmm.
And the performance decreased quite fastly due to radiation effects and so on.
Are those SNSPD detectors? Because you also have APD detectors, right? And from reading the paper, I got the understanding that APD detectors are potentially easier to put inside of a satellite compared to
that's true.
SNSPD.
Yeah,
is that because of the cryogenic components primarily,
exactly,
or is it something else? Okay.
Yeah, so that's easier, but still this is very challenging. In fact, to put an APD, and the problem is that if you work in uplink, you will need an APD with good performance over time, and so you have to maintain the performance, and so the APD avalanche photodiode should be resilient to all the space environment impairment. So.
Okay.
Yeah.
Understood. So we discussed two of the selection criteria now. We still have the orbit height, so maybe we can get into that one. Why a low Earth orbit is actually preferable for this kind of system?
Yeah. Okay, so you have to keep in mind that in quantum information networks, you cannot amplify the signal. So here, in this picture, this is a bit misleading because you can think about a very powerful laser that is embarked into the satellite, but this is not a powerful laser. In fact, this is a few nanowatts of light. So the beam is very, very weak by essence because this is a quantum. So this is single photons. Here, this is pairs of single photons, let's say. Pairs of photons that are emitted together. And so the light is very weak in energy and in power. And the problem is that the higher you are and the lower is the signal you receive at the ground.
Yeah.
So the lower the satellite, the better it is for the link budget. And the link budget is exactly what you get compared to what is emitted.
Are there any benefits with a higher altitude orbit? If it wasn't for this problem with attenuation in the signal, is there actually any benefit to having the payload in a satellite with a higher orbit? Or is this like a no-brain requirement? Okay. So could you maybe summarize what those reasons are? Or like what the benefit would be of putting it in a higher orbit, in a higher orbit if you could?
Yeah, so typically if you are too low at a too low orbit, you will not be able to connect Madrid and Berlin, for instance. So at some point, if you want to connect cities that are far away, you have to increase the altitude. In this configuration, where what you want to do is entanglement distribution from space to the ground. So you have to increase the altitude due to the visibility. If you want to increase the visibility, you have to increase the altitude. And also the higher you are and the higher is communication time. Because the higher you are and the lower is the speed of the satellite. So that means that so typically for GPS, global positioning system, we are using satellites at 20,000 kilometers, and so Galileo typically. And the Galileo satellites are sufficiently far away such that you have a significant time because you need to see 3 satellites at the same time. So you always have more than 3 satellites in visibility, and you see them during maybe 20 minutes, for instance. So the higher you are in altitude, and the higher is the communication time.
Okay, and I assume also, to begin with, I assume that in the GPS system, we also rely on optical communication between the satellites and, let's say, ground stations. If that's the case, the reason why we're now putting this at a low Earth orbit and why we have like issues with putting it into a higher altitude orbit, is that because you need to send an entangled state and therefore the requirement for 1 photon, or how is it that a GPS system can be on orders of magnitude further away from Earth?
Yeah, but the GPS does not use optical lights. Huh? There is no optical light.
Okay.
This is radio frequencies.
Okay.
So the link budget is very different.
Okay, understood.
This
Well,
is
my
another
apologies then.
calculation. Yeah.
Right.
And we can use also amplifiers. In our case, for quantum communications, you cannot use amplifiers. Otherwise, you destroy the information that is encoded into a single photon.
Okay, understood.
Yeah.
So then for the last requirement, or the last selection point, you have the wavelength as well. Would you mind explaining why you chose the wavelength that you did and what the alternatives would be for choosing another one?
Yeah. Okay, so first you have to think about what is the atmosphere, and the atmosphere is a mixture of many gases, and so the problem is that the gases absorbs some wavelengths. So there is some wavelengths that cannot pass through the atmosphere. So if you think about X-ray photons, for instance, that are bad for health, the good point is that ozone, which are 3 atoms of oxygen, they are like a shield for these wavelengths. So in the atmosphere you have some gases that absorbs some wavelengths and that does not absorb other wavelengths. And typically for space to ground or ground to space optical links, one good band or roughly or around 1550 nanometers or 1064 nanometers, or in the visible range or close to the visible range in 800 nanometers, so close to the near infrared. So you cannot decide, you cannot fix the wavelengths as you want. First you have to look at which wavelengths are not absorbed through the atmosphere. That's the first point. Then you have to select lasers that are compatible to these wavelengths, and that could be a problem, particularly for space applications. And then you have to also to be compliant with the wavelengths that could be detected by single photon detectors that you can find on the market. So you have many constraints from the atmosphere or technological constraints from lasers or detectors, and you have to find the good candidate of wavelengths. And so typically in the project we are discussing, people are looking at 800 nanometers or 1550 nanometers.
Okay.
Typically,
and those two are
typically
those two are the two relevant ones that you could potentially pick from. All others are more or less out of the question.
Yeah.
Okay, awesome. I think in terms of my questions for the theoretical implementation, we're actually at the end now. I know that I cut you off a little bit early last time when we were discussing sort of next steps for this kind of research. So if you want to present the last part of the presentation as well, and just briefly talk about what you think will be the next steps for this kind of technology, what you think maybe Europe needs to do as sort of a holistic, continent really, to promote this kind of development.
Yeah, sure. And particularly that's important because I'm working at Thales Alenia Space, and we need to find good engineers to work with us. And the problem is that there is no schools that teach all the skills required to work in our group. Because in fact, we can find people who are experts on quantum informations at the ground level, I mean, so they are not aware about the space, the space sector or the space components. And there is also we are working on quantum cryptography, so we need also people who are aware about cryptography. And there is also the atmosphere. So you can find a good candidate that has performed a PhD on quantum information, but who is not aware about all the impairment due to atmosphere. So that's complicated to find good candidates. And so what we are doing, we are training we hire in the group some new engineer, and in fact they are trained in our group directly, and after we can hire them definitely with a permanent position.
Mhm.
So the important thing to keep in mind is that if you look at a Capgemini report, Quantum Technologies, they have performed an assessment where they show that in industry there is many sectors that are very interested by the quantum technologies. And here at Right, what they show, what Capgemini study show, is that most of the people are beginners with these technologies. Some plans to include it in the near term, and some of them have already implemented some technologies, quantum technologies, and so the industry will need quantum engineer, in fact. And so far in school, in engineer school, people are not. They have some quantum skills, but they do not have deepened this skill. And so I think we definitely need in the universities or engineering schools more investment into the quantum technologies domain. So that's the first thing. And what I wanted also to share with you is that at the moment in Europe there are many projects, many activities related to space-based quantum communications. So for instance, there is a saga. The European Space Agency is a major actor, and the SAGA project is in fact the project that is defining the quantum cryptographic system for Europe in the Euro QCI initiative. We are also working in the TQuant project. So TQuant, this is for technology quantique, in fact. And here what we target is not only QKD, but also quantum information network. Mm-hmm. There is also IRIS Square for the secure communication of Europe. And Thierry Breton has explained that he wants to include QKD into this to securize our communications. We have also projects on quantum key distribution from a geostationary satellite. So this is very, very challenging, but not excluded. Mm-hmm. And next year, SES, who is a major actor, major space actor, will launch a first QKD sat called Eagle One, and this is also a European Space Agency initiative. Yeah, so here you see the curve. So this is the ESA invest on quantum, and so that's very good for us because this is a boost on the topic. Mm-hmm. And also the European Commission is working actively on this with the flagship with the Euro QCI for European quantum communication infrastructure that target both QKD and quantum information network applications. There is also OpenQKD, Petrus. There is a lots of projects that I do not mention here, so the list is not exhaustive, but this is important to mention at least these 4 projects.
Mhm.
And here in France we have the plan quantique, so this is 1.8 billion euros for the quantum technology during 4 years.
Mhm.
And also France QCI, France 2030, and the CNES with the French Space Agency invest on these topics, and they are our customer for many studies. And in Germany there is also investment, so 2 billion in quantum technology, and the Space Agency, the DLR, is also very active for space-based quantum information project. But maybe mainly QKD so far, but I think the thing will change also for them, and going towards quantum information networks. And so all these actors are actively involved. So ESA, CNES, DLR, us, Thales Alenia Space, of course, Airbus, OHB, and so we are working all together on many projects. So
Okay.
yeah, and outside there is also lots of initiative, like in Israel for the development of telescopes. In Canada there is KISAT. We are discussing with our colleagues. They will launch the satellite. So this is a CubeSat, and the launch, the target date is next year, so in 2024. In USA you have lots of things, but maybe more on quantum computing with the Quantum Gov initiative. But still there are some projects that target to include untanked photon source into the ISS. So they are also working on quantum entanglement distribution. In the UK also, Bristol is developing a 12 unit CubeSat, 12 liters, and the launch is also 2024. So many people are working on this. I have mentioned also Spectral in Singapore, and they are working on 2 satellites with target launch 2024-2025. And of course there is China with the leader on this topic, and they already have launched 2 satellites, Michus and Jinan-1, and now they have a ground network with more than 2,000 kilometers length, so that's quite incredible what they're doing.
Mm-hmm.
Okay, so this slide, what is important here is what in the paper we have published, we distinguish many phases, so resource stage, the network stage, and the build stage. And so right at the moment we are here in the development phase of the system, so this is we are developing the building blocks. And we have also our colleagues in research lab are working with quantum memories development, which is important for us, because otherwise it will be complicated to have a commercial service for the quantum internet. And then we target to go through the network stage in 2026. So we will see. We can discuss. We can do a check at this time to see if we are on time.
Uh-huh.
And so there is another slide that I wanted to show. I have mentioned the TQuants project. So this is an ESA-CNES project. And so in this project what we are doing, we are developing the quantum building blocks for the quantum information network system. Mm-hmm. And so we are developing space source, and so people are doing this. So the Fraunhofer Institute has already developed a source here, so this is a bulk source, and Aurea has started to develop. So Aurea is a company in France with whom we are working on TQuants, and we are developing a space source, space untanked photon source. And there is also QT Labs. So there is many companies are now actively involved in the development of this building block. And this is also the same for the ground station. So the ground station is a telescope on the ground, and the telescope can follow the satellite. And so in Italy there is Officina Stellare who is developing such terminals. In France we have OGS Tech. We are working with them also in Tquant. And the QT Labs is developing a prototype of compact telescope. And there is also the QKD modules for QKD application. And typically ThinkQuantum has already a good product, and ID Quantic also. So this could be emitters or receivers. This is you need both. Mm-hmm. And in the US, you have also QNect with a company that is developing many quantum information building blocks. In fact, they also developed the quantum memory. They have a prototype, the first commercial prototype of quantum memory can be sold at QNect in the USA. Mm-hmm. And in France, we have a startup, WeLink, who is developing also quantum memories that are required for the quantum internet. And so this is just a few examples of companies. There is a lot of other actors, of course. And all these people are now engaged in the race to the quantum information network development. Mm-hmm. So this is just to give you an overview.
Yeah.
Yeah, and finally, so the conclusion here is that so Thales Alenia Space is a major actor on this topic, and in fact, industry plan to use the quantum technology, as I said, and so the main message here is that industry will need quantum engineers, and so the young people who are finishing their study. This is a good news for them if they are interested by this topic, because I think many companies will hire such skills, such engineer with such skills. And so what we are developing at Thales Alenia Space is a European Quantum Cryptographic System, so EuroQCI. And we are actively working on quantum information network, which is called also the quantum internet. And in 3 years, I realized that we were 3 or 4 at the beginning, and now we are 30. So our group is actively growing, yeah. And also the number of projects is multiplied by a factor of 10. So this is a very attractive and active field in the quantum information domain. Mm-hmm. Yeah, so I don't know if you have any questions.
I would only have one more question, and that would be whether there are any initiatives that you're currently seeing in quantum information network development, but also perhaps the wider space of just quantum technologies that you don't think is getting enough attention at the moment, and where you think additional efforts would be required. That's the last question I have.
No, I think people have realized that the satellite is mandatory, and you know, in Europe we realize that for artificial intelligence we are not the leader, so compared to China and the US, and so we also realize that for the quantum race we have very good researchers and company laboratories. So we definitely could take the lead, and I think people have realized this in Europe. So I think now that's why we can find some customers to pay us for working on such a project, and I think also with QKD, quantum key distribution. We realize that due to the threat of the quantum computer, it is important to move to change our ciphering methods, and so I think we realized it, and now we are on the track to develop some new technologies on the based on quantum effects and quantum technologies, in fact.
Okay, good.
Yeah.
But then I suggest we close it here. Thanks a lot, Laurent, for taking the time to join and for presenting.
Yeah, you're welcome.